How's it going, everyone? Jim Sullivan here, just in case you didn't know. I figured we'd talk about a fun forecasting challenge in winter here in Ohio, all of the state, not just the Cleveland office downwind of Lake Erie. Convective snow showers, we see them several times a winter, and they can be impactful at times. They were very impactful on Friday. Some areas west of Cleveland saw 7 inches, which even I didn't expect. And you guys know I'm a pretty big snow weenie, so if I don't expect it, it really is a surprise. All right, so let's dive in. Most of you should know what they are. In fact, you all probably do, but just in case you don't, a lot of times these are like summertime thunderstorms, brief bursts of heavy precipitation, in this case, snow. And, a lot of times they don't drop a lot because they're moving so quickly, but drivers hate them. This is when you get your freeway pileups when people are clipping along at 70 miles an hour. All of a sudden it's a whiteout. They can't see, the road's covered. And a lot of times they're under forecasted by the Weather Service and a lot of other agencies, or they just put snow showers in the forecast. And, that's kind of misleading. So I'm going to go through the processes that I go through. I'm going to share them with you when I'm looking for these types of things in the winter when I'm putting together my forecast. So if you're making your forecast, there's a few things that if they kind of align, you need to look out for this. A lot of times these occur in cold air advection regimes. A lot of times there's an upper trough ahead with cold air in the mid and upper levels of the atmosphere that makes things a little unstable. A lot of times you have something to trigger it, another cold front or a short wave. A lot of times you'll get a big cold front to come through, and then like the next day a little dinky front comes through and fires off these 10-minute whiteouts. And obviously they're going to be occurring in winter. So kind of alluded to it, you need some instability, and when the atmosphere is unstable, the lapse rates are steep, and we'll look into more of that in a few minutes. And you need some moisture, obviously, to wring it out. I mean, if the atmosphere is unstable, but there's no moisture, the air will just rise, and you'll get more dry air. And you need a trigger to set the snow showers off. Sometimes you can get these in cold air advection regimes, but they're not quite as organized. Usually, if you have a trigger, you increase your odds of seeing these convective snow showers. So we're going to start off by looking at what happened this past Friday. It was a great example, then we'll go from there. Okay, so I'm sure most of you guys, when you put together your forecast, you're looking at some QPF output from the models. And this is a good starting place. The way you'll identify these schemes where you can get snow squalls is you'll see QPF on the models, and when you see QPF on the models, you always have to say, why is it producing QPF? What's causing this? So if you're going through that process and you notice some things, that's when you need to know, okay, maybe these snow showers can be a bit heavy, convective, maybe some thunder, never know. So the issue is the models usually will not explicitly show this. They'll just give you signs. We're going to go through some of the main models leading up to this past Friday event. Here's the NAM a couple days out. It shows a swath of 3 to almost 6 inches in southeastern Ohio. That's wrong, but at least it shows something. But as we thumb through the next few runs, it doesn't show much of anything. Then finally, the 0Z run the night before kind of showed something, maybe 2 inches or 3 inches in north central and northeastern Ohio, which was still way off the night before. The 6Z run the night before, okay, it's getting the placement better. This ran from Cincinnati to Dayton to west of Cleveland, so at least it's kind of getting the placement down. Amounts way too low still. Then finally, the 12Z run the morning of kind of got the amounts right. Maybe it was still low in parts of the state, especially central and southwestern Ohio, and it was too far east with the snow band the morning of. So the NAM, next to useless, other than showing glimpses of the potential, I guess. GFS, not much better. Here's the 0Z GFS run the night before. It's okay with the placement, kind of, maybe better than the NAM was, the 0Z run the night before, but way too low on the amounts. 6Z run the night before, better with the placement, I guess, but still too low with the amounts. And finally, the 12Z run in the morning, the juiciest run of the GFS leading into this 7-inch snow event, only showed 1 to maybe 3 inches. It was okay with the placement, if anything, a bit too far west, but at least it was in the ballpark, but way too low on the amounts. And the high-res models, not a ton better. 0Z, 4-kilometer resolution NAM run the night before, showing a tenth to locally a quarter inch of liquid, which translates to about 1 to 3 inches of snow. Doesn't show nearly enough snow in the Cincinnati metro, where they saw 2 to 3, locally 4 inches with some thunder. 6C run is better. It shows a little bit more, a slightly larger area, getting over a quarter inch of QPF, but still too low. Its placement was kind of there, at least in the southern half of the state. Northern half of the state, it was actually too far west. And the 12Z run the morning of suggested peril for the Cleveland afternoon rush. It got the liquid amounts right the morning of, about half an inch in a narrow swath, but it showed it occurring over Cleveland. It really happened 30 miles farther west. Here are a couple of WRFs, the NMM and ARW. NMM on the left, the 0-0 on the night before is kind of in the ballpark with amounts. Shows a swath of over half inch of liquid falling, which would imply up to half a foot of snow, which happened, but it was too far east. ARW on the right, too dry. Morning of, both models are better with the QPF. The NMM is actually a bit overdone, and it's off with placement. ARW is better with placement, still too far east, and just a little underdone on the QPF. Not terrible. These models do have use, even though people hate them because they tend to run a little bit juicy. But they are useful for picking out things like this, although they weren't very much help this morning either. So you're going to see this QPF on the models, and you're going to start looking deeper and go, okay, the models are showing some QPF. Why? And we know that the models don't resolve this sort of stuff well, but you can kind of see the high-resolution models are going to give you the best idea. So this might not be much help 2-3 days out looking for model QPF for these convective snow shower situations, because it'll be underdone on the GFS and Euro. They're too low resolution to resolve those 5 to 10 mile wide snow squalls. They won't resolve that properly. So high-res models are your friends, but before you get into range, what do? Well, you look for certain things that I'll point out to you in a second. And once you're in high-res model range, you still can't take them verbatim, word for word, exact, because they're still not good, but they'll give you a better idea of what you'll be looking for. So we're going to use today as a textbook type example of what to look for, and then I'll give you one more subtle example that kind of shows you why you need to look at SKUTs when you're forecasting these things. Hang tight. All right, so you're going through making your forecast. You see that the models have QPF, so you want to look deeper into it. You want to know why. So today's example was just a textbook example of convective snow showers. You had a low pressure over the lower peninsula of Michigan. You had a strong cold front extending down, pushing into Ohio. There's your trigger. Strong cold advection behind the cold front, so cold air advection regime. So at the surface, it looked pretty good for maybe convective snow showers today. But again, you have to look at the surface and aloft. Looking aloft, oh, trough aloft, right overhead. And it was very cold aloft under that trough. Now, you usually want to see a mid-level shortwave. Today, you had this full-blown vortex moving into Ohio. This was 12Z, 7 a.m. Friday. Snow was starting to break out in Kentucky at this point, and then it would shift northeast as the vortex sort of kicked east. So the basic things we have trigger, cold advection regime, upper trough aloft, and a kicker, a shortwave rounding the main upper trough. Very cold aloft in the middle levels of the atmosphere. This is that's a patch of minus 36 degree Celsius area at 500 millibars. That is very cold even in the dead of winter. Cold aloft, so that means steep lapse rates, which we'll touch on more. Now, you can see the short wave here at 700 millibars, clear as day. It's closed off. Very good mid-level jet rounding the base of this, and you can see northern Kentucky, southwestern Ohio, kind of on the nose of this low-level jet. So that means there's convergence there. Usually below 500 millibars, you want convergence. If you want precipitation above 500 millibars, you want divergence. So where on the nose of these low to mid-level jets, the air piles up, so you get convergence. So that checks out. Let's look at the temperatures this morning. 700 millibars, cold air advection, very cold air at 700 millibars, trying to filter in. You can see it's warmer here, colder here. Winds are blowing the cold air towards the warm air. That's cold air advection. 850 millibars, clear as day shortwave. Decent low-level jet rounding the base of it. You can see maybe a little bit of convergence here on the nose of it, where the snow was breaking out at this point. Definite cold air advection at 850 millibars. Look at this. Go from around -5 degrees Celsius, 850 millibar temperatures over parts of southwestern Ohio to -22 or colder over western Illinois. That's a pretty short distance. That's decent cold air advection. Now, so that's what a classic situation like today's will look like. You'll get, let's go through it one more time, just one summary. You have some sort of a trigger. This was a blatantly obvious cold front. You want it to be in a cold air advection regime. You usually get shallow instability in those situations. That's why cold air advection regimes are better for these. Warm air advection regimes, the instability is usually elevated, which in winter with snow showers usually won't work out. You can get overrunning snow showers for sure, but they won't really be as convective in nature. The lifting mechanisms are a little different. Cold trough aloft, and then there's your secondary shortwave moving in beneath that cold trough aloft, and that's just a closed off void that was very potent. You can see cold in the mid levels, clear as day shortwave at every level we looked at, and clear as day cold advection at every level we looked at. So those are kind of the things you'll notice on the models in these situations. And in a minute, I'm going to show you, actually next, it's going to be a few minutes for me because I'm going to take a break here as soon as I get done talking about this slide. We'll look at what the model showed leading into today. So even though the models weren't right, there were still some of these signs on the models, and I want to show them to you. All right, before I go any farther, I just want to make sure you can easily identify these key features on the weather map. A cold front, you'll see a shift in winds. You can see southeasterly here, west-northwesterly here, colder air behind it, warmer air in front of it. And you'll see a nice kink in the isobars along the cold front. It'll usually be attached to a low-pressure system. Troughs aloft, you'll just see a large area where these black lines, they're called geopotential height lines, kind of indent to the south. And you'll usually see a nice jet stream rounding the base of that trough. Short waves in the middle levels of the atmosphere, again, you'll see an indentation in these height lines. This one was closed off, it was so potent. And you'll usually see a lobe of vorticity associated with it. Temperature plots, I think you can read. Again, shortwave, indentation, this one's closed off. This is a better example of a shortwave. There's an indentation that isn't completely closed off. Cold air advection, just want to go through this really quickly. Here's how you can tell where cold air advection is going on. You can see this temperature gradient here, say across Indiana, and the winds are blowing across that gradient from cold to warm. When that happens, you have warm air advection going on. So if you see these key things going on the models, I like to look a little at a few certain things that really help tip me off personally. First one, this is the NAM from last night. It was off with the snow, but it still showed some ideas here when looking deeper. First things first, 500 millibars, you can see the shortwave moving into Ohio, check. And over this region of Ohio, there's positive vorticity advection going on. That means this area of higher vorticity air is moving into an area of lower vorticity air. That just, higher vorticity means the air just has more horizontal spin to it. When positive vorticity advection occurs, that means the atmosphere, there's more lift going on. Positive vorticity advection is a lifting mechanism. Where it's occurring, you need to be on the lookout for heavier precip rates. I like looking at the 700 millibar and 850 millibar vertical velocity plots on the NAM. The GFS and Euro won't show this well. They'll usually show a broader area of less intense vertical velocity. But if you're looking at the NAM and you see sort of splotches of stronger vertical velocity, that's a sign that convection is a concern, especially if all the other factors are lining up. You can see this is occurring right out ahead of the shortwave where it should be. And I also look for moisture up to at least the 700 millibar level. If you don't quite get it to 700 millibars, it's not the end of the world, but if you're getting moisture to 700 millibars and vertical velocity at 850 and 700 millibars, you're in good shape. And you can see there's plenty of moisture over Ohio Friday with these convective snows. And again, at 850, you can see the sort of splotchy vertical velocity indicative of convection. So if you see that on the models, the big features I pointed out that you need, and then the smaller features, the positive vorticity advection right ahead of the shortwave, and then the vertical velocity in the mid-levels of the atmosphere right ahead of the shortwave to go along with moist air into the mid-levels, you're really good to go. Now, humidity at the 700 millibar level isn't a direct requirement, and we'll get into that more in a minute, but if you're getting humidity up to 700 millibars, you're in good shape. All right, so you're going through. You've identified the big features on the models that you're looking for in these situations. A trigger at the surface, usually a secondary cold front pushing through, a cold trough aloft, a short wave in the mid-levels, and from there you want good positive vorticity advection in the area of interest. You usually want the NAM to show some signs of splotchy vertical velocities at 850 millibars, 700 millibars, and if you have moisture up to 700 millibars, you're good. Here's another big tip-off, lapse rates. Let's go through what lapse rates are really quick for anyone who might not know. The lapse rate is just how quickly the atmosphere cools as you go up. Now, there are a couple of special and very important lapse rates called the saturated adiabatic lapse rate and the dry adiabatic lapse rate. Saturated adiabatic rate, that is how quickly a saturated parcel of air will cool if you lift it. That lapse rate is 1.5 degrees Celsius per every 1,000 feet you lift it. The dry adiabatic lapse rate is about double that. It's about 3 degrees Celsius for every 1,000 feet. Any parcel that is not saturated cools at the dry adiabatic lapse rate when you lift it. So, if the environmental lapse rate, and you can determine the environmental lapse rate just by looking at certain pressure plots on the models, or plots at different pressure levels, like 850 millibars, 700 millibars in surface. And I gave these numbers in Celsius because almost all of those mid-level temperature plots are in Celsius on the models. Usually in these situations, if you're going to get convective snow, the atmosphere will be conditionally unstable in these ranges. Basically, if the environmental lapse rate is lower than the moist adiabatic lapse rate, the atmosphere is stable. It's very hard to get convection in those situations. Sometimes you can if you get a really strong front to push in, and if that happens, maybe you will get a burst of snow along the front, but if you are absolutely stable, you don't need to worry too much about it. Be mindful, but you don't need to worry too much. If the environmental lapse rate is greater than the dry adiabatic lapse rates, the atmosphere is considered absolutely stable. If it's in between, it's conditionally unstable, which just means if you get a parcel of saturated air, it'll cool, or it'll become unstable if you lift it. So dry air will not be unstable in a conditionally unstable environment. Moist air or saturated air will be, and that's why you need moisture in these situations, is usually you're conditionally unstable. So write these down. This is a quick little cheat sheet for conditionally unstable atmospheres based on temperature differentials between certain levels. Let's check on Friday, or today's event. It's still Friday for me. Near Akron, Canton at 2 o'clock, surface temperatures were pushing 40, around 4 degrees Celsius, 850 millibar temperatures, 6 below 0 Celsius. Check. That's a 10-degree differential. Surface at 700 millibars, 21-degree differential. Check, check. Surface to 500 millibar differential is 39 degrees Celsius. And if you ever get a temperature differential between the surface and 500 millibars pushing 40, you are in the play for some thunder. Now, if you're unstable using the surface to 500 millibar temperature differential, you're going to want to check Oh, that's not what I wanted that to do. You're going to want to check these lapse rates too, because if one of these doesn't check out, that means there might be an inversion somewhere between about 700 millibars and 500 millibars. And if that's the case, you won't get parcels rising freely to 500 millibars and higher. Today, these both checked out. So today, the lapse rates worked. It was humid up to 700 millibars and higher. The models the night before did a good job of showing that humidity. They did a good job of showing the lapse rates. They'll usually show these well in advance. They did a good job of showing the upper trough overhead, the shortwave overhead, the positive vorticity advection overhead. So if you saw these clues on the models last night, or even beforehand, the models showed this, you would have said, okay, there could be some good bursts of snow today. Now let's look at a much more subtle case from November of 2013. All right, so we just got done looking at a convective snow situation that dropped locally over half a foot. It was blatantly obvious. You could have figured it out looking at the basic model plots. No skew T's, no buff kit. This one's a little different. Now, let's look at the big picture first and see if you can still pick out the subtle features. We have a little cold front moving through. This was Saturday the 23rd. This was Ohio State was playing some irrelevant team in Columbus this day, and a couple of snow squalls pushed through during the game. This is valid 1 in the afternoon. You can see cold front, check. And there is some cold air advection. You can see in the 20s to near 30 here, and by the time you got into Kentucky and Virginia, temperatures pushing 30s and 40s. So there's cold air advection, a cold front, that checks out. Let's look at 500 millibars. Where's the shortwave? Is there a big shortwave moving into Ohio here the morning of? No. This little ripple near Lake Michigan is our shortwave. Very, very subtle. Now, there was some vorticity associated with it, so vorticity plots are important. 700 millibars, you can see it a little better. Not blatant, but it is there. Now, look at the 700 millibar relative humidity. Here's the shortwave. Humidity is like in the single digits over much of the Great Lakes. Here's the highest humidity associated with the system, pushing 50%. That's really quite dry. So if you're looking at the 700 millibar RH plots and it doesn't check out, this is why you need to look at skew T's or buff kit, and we'll give you a crash course in skew T's in a second. Here's 850 millibars again. You can see a little shortwave. Not much, but it's there. Not much more humid. You can see it is a little bit more humid along the shortwave axis at 850 millibars, and that ultimately ended up pushing into Ohio, which is why we were able to see some snow. But this one isn't as obvious, just a little baby shortwave. Very dry in the mid-levels of the atmosphere. But everything really is in place except for the humidity. You got the cold front, cold air advection regime, trough aloft, shortwave aloft. But with this event, even the NAM didn't spit out much snow with this system, which is why it never hurts to pull up buff kit, or if you don't have buff kit, go to a site for model output that has skew T's available for you to look at, and we're going to look at a skew T now. All right, so when you're forecasting for convective snows, or really anything, skew T's are your friend. Buff kit makes life easy. Unfortunately, I am technologically challenged, and I don't have buff kit up and running on this laptop. And you might not either, so I'll go through how to read a bare bones skew T. Buff kit again makes it easier, but I'll give you one that's not buff kit. So first things first, these numbers on the bottom represent temperatures, and these lines going from left to right diagonally represent lines of equal temperature as you go up. So say you're here in the atmosphere on this black line, it's 30 degrees Celsius. These temperatures are in Celsius. Most skew T's will be in Celsius. You'll need to learn that conversion. I'm not going to go through that with you. I think most of you know it. All right, the red line is temperature. The green line is dew point. So this skew T is from the event that I was just showing you, a very subtle event. You might not have seen it or maybe thought it was too dry for precipitation until you pulled up a skew T. because 700 millibars, bone dry. Wow. Let's go through the rest of these lines before I really delve into this. These lines going from right to left at about a 45-degree angle, those are the dry adiabatic lapse rates. So a dry parcel lifted will cool at the rate of these lines. These dash lines going from, yeah, there we go. Also from right to left at a much slower angle, those are the moist adiabatic lapse rates. And these dash lines going from left to right are the dew point lapse rates. That's the dew point lowers much slower as you increase in height in the atmosphere. So let's do some basic skew-T work for this convective snow situation. That dropped a good dusting on parts of the state. Parts of northern Ohio saw 2-3 inches with some help from Lake Erie. So as you could see from the big picture images, this event doesn't stand out. The NAM didn't even spit out much QPF with it. But you can see the temperature, you can read lapse rates really nicely on a skew-T, is almost, the environmental lapse rate below 800 millibars is almost as steep as the dry adiabat. So it is definitely conditionally unstable below 800 millibars. And you can see there's a nice zone of saturation going up to about 850 millibars. That is key because find the -10 isotherm, degrees Celsius isotherm, and make love to it, because between the -10 degree and -20 degrees Celsius isotherms, that is the snow growth zone. You need to get lift and moisture into the snow growth zone in order to get snow. If you don't, you won't get snow. In general, you usually want to get moisture up to about 5,000 feet above the ground to get good-sized showers that can produce decent precipitation. If you don't, you'll get flurries or nothing. In this situation, we just barely got there. That's about 5,000 feet above the ground here in Ohio. So let's do some skew-T work. First things first, if you aren't on a skew-T site that draws in these lines for you, you'll need to do it by hand. Take the air at the ground, cooled at the dry adiabatic lapse rate. Then take the dew point and cool it at the dew point lapse rate. You just follow the lines I pointed out. Once those two lines meet, cool the air at the saturated adiabatic lapse rates. The area in between that I'm kind of shading in now, that is your instability. And you can see on the skew-T you have instability into the dendrite or snow growth zone, more than 5,000 feet into the air, and moisture in that area. That sounding tells me that if you get a lifting mechanism, which we had that day at Cold Front, that you can still get convective snow showers. This is why skew-Ts are very important, and that's a crash course on how to use them. And that they're very helpful in any situation. Lake effect snow, thunderstorms, winter precipitation types. Very, very useful to know how to read them. Alright, so now that I went through what to look for on the models, let's go through a few good model websites that I like to use. Holy shit. I know what I'm doing while this is uploading to YouTube. My math homework. I'm doing my math homework, you perverts. These are all decent websites. You can get lots of information from them. The College of DuPag, I think I pronounced that right, website, weather.cod.edu is my personal favorite. Most of the model maps I showed earlier, except for the snow output, were from this website. Point-and-click skew-Ts for the RAP, NAM, GFS on both COD's website and Twister Data, which is just an amazing tool. You can also go to Earl Baker's website, WXcaster, for skew-Ts. You have to search a little bit, but the skew-Ts are on there somewhere. Coolweather.com, coolwx.com. I used this a lot when I was younger, and sometimes I still do when I get lazy. If you want to look at, say, the NAM forecast relative humidity in all levels of the atmosphere for the entire run by time in just a nice little graph, CoolWX is your answer. If you just need a quick glance, CoolWX is great. The PSU eWall has a lot of great models, has some of the high-resolution models, the high-resolution NAM. GFS ensembles, other stuff that you might use for other forecasting endeavors. The Weather Underground has the most Euro data that you'll get for free, including QPF output, surface temperature output, etc. And there's always NOAA's website. All these websites are free. You can get all the information you need from these websites. There are other paid websites that have their benefits, and let's move on and get this image off our screens. All right, we are almost done. I appreciate you sticking through me. It's been a good half hour, about 4 hours for me putting this together. So, just a quick summary of what you want to do when you're looking for these convective snow showers, which, again, can be very hazardous to travelers. Your forecast viewers need to know about them if they look likely to happen. You can't just say light snow showers in the forecast. No. So you're looking at the model, making your forecast. It shows precip. You want to know why it shows precip. You should always know why it shows precip because that'll tell you if it's realistic or not. Sometimes, in rare situations, all the models will be dry and you'll still get a convective snow shower setup, but that's rare. Usually the models will spit out at least something. Once you're looking into it, look for a trigger, usually a weak cold front at the surface, or strong, and at least a modest shortwave in the mid-levels of the atmosphere, underneath a cold upper level trough. Then you're going to want to look for moisture into the dendrite growth zone or snow growth zone and steep lapse rates into that area as well. That can be done using SKUTs, which are your friend, or just by looking at the pressure level plots on the models. And if you decide that convective snow showers are likely for the area you're forecasting, forecast accordingly. Again, I made this specifically for my NeoWeather colleagues because every once in a while we love sharing forecast ideas with each other, and I'm sure they'd love to know what goes on inside my mind because my forecasts are all over the place and off the wall. But I'm putting this on YouTube for anyone to watch who is really bored, so do whatever you'd like. Here at NeoWeather, it's hard for us to fit onto a graphic, scattered snow showers, could be briefly heavy, up to an inch of accumulation, which is what a lot of times happens in these convective snow shower situations. It's hard to fit that on a forecast graphic. We have other forecast products. We have a text forecast blog where we can type out our thoughts. We're supposed to every day. And we can put more information there. We post our graphics to Facebook. We can post more information in the photo caption. So there's a lot of ways for us to communicate this to our viewers. And if you're not with NeoWeather and you're watching this, maybe take those ideas, whatever. In most situations, you won't get half a foot of snow like what happened west of Cleveland today, January 17th, 2014. Usually it'll just be, passing showers that drop maybe an inch or so. But that's still hazardous to drivers. They still need to know about it. You can't just say snow showers in your forecast. You need to tell them somewhere that it could be heavier. Now, if it's a situation like today where everything's off the charts and you have a huge trough, a huge shortwave that's closed off, when you get a compact vortex, that's when you might see a more concentrated area of heavy snow. Usually that won't happen, but if you see that, keep it in mind. Usually it's less, but I can't tell you how to forecast, but if you see these factors coming together, just forecast accordingly, and everyone will be happy. All right, thanks for watching. I appreciate it. I took a lot of time putting this together, and if you're listening to me now, you really stuck through, so thank you. Have a nice day, night, weekend, whatever it is for you.